When we think about industrial piping, it seems pretty simple, right? Just a bunch of tubes to get liquid from point A to point B. But what if I told you that for one of the most vital pieces of equipment out there, the pump, the design of its inlet pipe is governed by a whole different set of rules. Rules designed to stop a violent, self-destructive process from ever starting.
See, in any processing plant, pumps are the absolute workhorses. They're the powerful hearts that keep everything flowing, moving huge amounts of fluid with incredible force. They are built to be tough, powerful, and absolutely essential.
But here's the crazy part. For all their strength, these pumps have a major weak spot, and it's right at their inlet. The entire design of the pipe leading into the pump has to be built around protecting this one single point from a very specific danger. Okay, let's dive into what that is.
That danger, the hidden villain in this whole story, has a name: cavitation. And it is a silent destroyer. It can literally tear a pump to shreds from the inside out, and avoiding it is the #1 mission of that pump suction pipe.
So what on earth is cavitation? Well, imagine you could boil water without adding any heat. That's pretty much what's happening here. As the liquid gets sucked into the pump, it speeds up, and the pressure can drop so low that the liquid spontaneously boils, even at room temperature. This creates tons of tiny vapor bubbles.
And this all happens in a really destructive cycle. First, the pressure drops, and those little bubbles are born. Then, they get swept into the high-pressure part of the pump, where that pressure spike instantly crushes them. We're talking a violent implosion. Each tiny collapse unleashes a microjet of fluid that slams into the metal impeller. It's like a microscopic sandblaster, just chipping away at the metal over and over and over.
To fight this, engineers have a secret weapon. It's a critical measurement called net positive suction head, or NPSH. You can really just think of it as the pump's lifeline. It's the extra buffer, that safety margin of pressure, that makes sure the liquid never reaches that low-pressure boiling point. If your NPSH is high enough, cavitation simply can't happen.
And I want to be really clear here, this isn't just some minor detail. It is the most critical factor when you're designing that suction pipe. The whole game is about protecting that pressure safety margin. So, the big question is, how do we actually do that? Well, there are two main lines of defense.
Our first protector is kind of simple: a strict speed limit. To keep the pressure high and stable, you have to deliberately slow the liquid down before it even gets close to the pump.
Now this is what I find so interesting. Just look at the contrast on this chart. On the discharge side, the pipe leaving the pump, we can let the fluid rip pretty fast. But on the suction side, we keep the velocity incredibly low. And why? Because of a basic rule of physics. The faster a fluid moves, the lower its pressure drops. So we slow it down on purpose.
To put this in perspective, a typical maximum speed is about 1 meter per second. That's about the speed of a slow walk. It feels totally counterintuitive, right? In a high-performance industrial system, we have to move things slowly. But yeah, that deliberate slowness is the absolute key to keeping the pressure up and protecting that precious NPSH.
All right, so let's move on to our second protector. This is where it gets even more clever, because it's not just about speed. It's also about the actual geometry of the piping. The shape of a single fitting can be the difference between a healthy pump and a dead one.
Okay, so the suction pipe is almost always bigger than the pump's inlet. To connect them, you need a fitting called a reducer. And you've basically got two choices: a symmetrical one, called a concentric reducer, or an asymmetrical one with a flat side, called an eccentric reducer. For pretty much any pipe, this choice doesn't matter much. But for a pump suction line, it is absolutely critical.
And this is just brilliant engineering. If you use that symmetrical cone-shaped reducer, it creates a little high point at the top, a perfect trap for air or vapor bubbles to collect. That trapped bubble will cause all kinds of turbulence and starve the pump, which leads to, you guessed it, cavitation. But by using the eccentric reducer with its flat side on top, you create a perfectly smooth, level highway for the liquid. No air pockets, no blockages, just a smooth, steady flow and a very happy pump.
So when you put it all together, the slow speed and the smart pipe geometry, you start to see the whole strategy. Designing a pump suction line isn't about moving fluid as fast as you can. It's about delivering it to that pump as gently and as stably as possible.
These aren't just some boring rules from a textbook. They are a masterclass in preventative engineering. Every single decision, the pipe size, the speed, the shape of the fittings, is made to fight that one specific threat.
And by getting it right, engineers make sure the heart of the plant keeps beating reliably for years and years.
It's a perfect example of how the most important design choices are often the ones you never see, the ones quietly stopping disasters before they ever get a chance to happen. It really makes you wonder, right? What other invisible engineering rules are out there working behind the scenes to keep our whole world running?